Hi again. As you noticed in the last recording, when we did in very different parts of this problem analysis through contour volume approach, we found out that there is an easy and direct way to find an expression for the height, h. We couldn't find an expression for the entire profile using contour volume analysis, but it could give us an exact direct expression for h. And that expression was exact, and it was valid for all values of contact angle, alpha. And it was this expression, a square root of sigma over rho g multiplied to 2 times 1 minus cosine of alpha, which can be rewritten as h being equal to, again, I can bring a square root of sigma over rho g out as a capillary length, and the rest would be inside the square root, which is 2 times 1 minus cosine of alpha. And this expression, which is valid for all different alpha, was not exactly the same thing that we found through an alternative approach to solve this problem. The alternative approach to solve this problem, which was based on writing hydrostatic balance for pressure and also applying Young-Laplace equation at the interface to find the jump in pressure that we get as we cross from air into water, gave us a differential equation. We solved that differential equation. We found the profile, overall profile of the meniscus, y as a function of x. At x equal to 0, we equated the slope of that profile to the tangent of the contact angle, tangent of alpha. And that expression gave us that height, h, of the puddle at x equal to infinity, the same parameter that we had in the contour volume analysis, should be capillary length, but multiplied to a different trigonometric combination based on alpha, multiplied to tangent of alpha. We call this solution to be approximate because of the initial approximation we made for the curvature, mean curvature. Now let's see whether these two really are the same or not. Definitely the exact solution for h should be valid for all alpha. So let's see, indeed, if alpha goes to 0 for a small alpha, we can actually recover the other approximation that we have. In the limit of alpha going to 0, so as alpha goes to 0, we can clearly think about expansion of trigonometric functions, namely the fact that cosine of alpha is approximately, for small alphas, using Taylor series, 1 minus alpha squared over 2. So I can clearly replace cosine of alpha with that. So h becomes approximately L cap multiplied to square root of 2 multiplied to 1 minus alpha squared over 2, which is only alpha squared over 2. And it's 2 and 2 cancels. The square root of alpha squared becomes alpha, so it becomes simplified to L cap multiplied to alpha. At the same time, I know that, again, for alphas that are much smaller than 1, sine of an angle is approximately the same as the tangent of that angle, and it's approximately equal to alpha, the angle itself. So capillary length times alpha can be written actually as, or expression can be rewritten as, in the limit of alpha small, the height of the puddle h can be approximated as L cap multiplied to tangent of alpha. And this is exactly the same expression that we had through the approximate solution. So indeed, we see that the solution that we got from contour volume analysis, which is exact and valid for all values of alpha, in the limit of very small alphas, leads to something that is exactly equivalent or exactly similar to what we got through the alternative solution, which was based on the assumption that alpha is very small. The alternative solution has this advantage. It's true that it's only valid for small alphas, but it has the advantage that it also gives us an idea about the overall shape of the profile. But you can see that, as we already know in this course, physics should give us a unique answer finally. No matter what method we take to approach a problem, our final answer in the right limit of approximations that we have used should be very much equivalent and similar to each other, regardless of the method that we have chosen. This was what we wanted to do in this recitation, and I stop here. I really encourage you to watch some of the movies and demos that we will do after this video, and I hope you enjoy all of them.